Hello everyone, thank you for joining us today. I am Guillermo Varela from Magni Europe, and I'm here with Guido Cherici from Elastico Disegno. Today he will show us the robotic hand design, Mia Hand, and we will see how it was designed with sub-D modeling in Rhino and PTC Creo, and how they use Rhino and Grasshopper for the customization. Remember that in the last 15 minutes of this webinar, we will have some time for Q&A, so you can ask questions in the chat, and we will check them at the end. Also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel where you can find more webinars and tutorials. Thanks again, Guido, for accepting the invitation to this webinar, and please start with the presentation if you are ready. Thank you.
Thank you, Guillermo, for the introduction. Thanks to McNeil's for hosting us here today, and of course to Delia that made all this happen. Welcome to all of our viewers. I'm Guido Cherici. I'm one of the partners of Elastico Disegno, and we are a design studio based in Turin, in Italy, and Elastico Disegno was founded in 1998. And our offices are just a short drive from the city. We feel that the countryside offers the right quiet and inspiration for our work. Here we have our offices, we also host workshops and work sessions with our clients. We work with many different clients on a wide range of products. We go from coffee machines to cash registers, from industrial kitchens that you can find, for example, in Michelin-starred restaurants, to cable reels, from medical devices to toys, dental floss, and all the way to perfumes and stores. So a very wide range of clients and products. Today, I will walk you through an amazing project we worked on, Mia Hand, which is a prosthetic hand for amputees. I will show how we approached the project and the role that Rhino played in this process, together with other softwares too, like Guillermo mentioned. Mia is a product of Prensilia, a company that started as a spin-off of the Biorobotics Institute of the Scuola Superiore Sant'Anna in Pisa. They're one of the leading research institutions in biorobotics worldwide. So let's start with, let's call it a far, far away reference for a project like this.
It is useless to resist. Don't let yourself be destroyed as Obi-Wan did.
Today, we're still far, far away from Luke Skywalker's hand. Most prosthetic hands on the market optimize the mechanical function, but leave the task of water and IP protection and aesthetics, usually to a simple glove, usually black or skin-colored, which work very well, mostly at highlighting that person's disability, not just at covering the hand. So our design process started with meeting with amputees, understanding how they use their prosthetic hands and the issues they encounter, both physically and emotionally. So this defined our product design guidelines. And the main issues that we found were the difficulty fitting the protection glove, the one that gives protection from dust and splashes, the weight of the prosthesis, and the duration of the battery. So we worked with the manufacturer, with Prensilia, also understanding and optimizing the internal components, because these hands has 3 motors, has a set of mechanics, a PCB, some electronics. So we took all this information and developed a concept that uses a lightweight open frame protected by an open finger glove. Think of the gloves used by cyclists that cover the hand, leaving the fingers exposed. This way, it was much easier to fit on the prosthesis for the amputee, and at the same time provides the adequate IP protection. And we also introduced the concept of a user-replaceable customizable cover, which we'll see more about a little later. So the design was able to retain two of the main keys, the main focal points of our project. So have a hand that retains a human proportion, but that still doesn't try to mimic a human hand, doesn't try to look like a human hand, because it's not. And with the added value of an easier to replace glove and possible customization. So the design was the natural consequence of the user needs and of the mechanical performance of this device. When we started developing this hand in 3D, it was 2018. So sub-D within Rhino still not here, and so we used T-splines. Today we would have used the sub-D within Rhino. And so with T-splines and sub-D modeling, we were able to fit our skin onto the mechanics, and at the same time working with the engineers to optimize some components placement to be able to achieve and retain these human proportions they were looking for. And it was sure no easy task, considering that, for example, the thumb contains a motor and a gearbox, so that's pretty bulky. And the index and middle fingers are the same, while in a human hand they are different sizes. In this case, they had to be the same size because they both host a whole set of sensors on the inside. And so we achieved a series of concepts that we presented with Rhino, and we were usually rendered with V-Ray. At this point, we had some concepts that the client approved, and that moved on to the next phase. And in this case, both our studio and Princilia, our client, work with Creo parametrics modeling software by PTC. Working with sub-D modeling meant that we didn't have to start from scratch in Creo after all the modeling we did in Rhino, but using a OBJ as a translation format, we were able to export all the sub-D geometry from Rhino, import it into Creo, which has a feature which is called freestyle, which can import OBJ meshes and sees them as native Creo geometry. So we were able to carry over all we did in Rhino as a matter of modeling, and retain it within Creo and use it for further development. Even though all parts were designed to be injection molded, the production volumes for a device like this are, well, luckily on one hand, are too low to justify such investments. And so we identified the jet fusion technology by HP as a perfect match for producing these parts. They use a PA12, a very strong and durable plastic, which was used for the frame and for the covers. The glove is cast in silicon, and we used the HP printer to 3D print the molds for casting the silicon parts. This is the silicon glove. This has also allowed Princilia to periodically receive user feedback from the amputees using this device, and rapidly implement the changes, make adjustments with no impact on tooling, because there's no tooling. The only downside at the time was that, this was 2019, was that the color options for the 3D printed parts with jet fusion printers were quite limited, because the parts come out of the printer in a kind of like dark gray color. It can be tinted by immersion, and so you can have all variations of gray, dark gray, or black. So not that many options. And so the customization that we were thinking of, which was mainly in the replaceable covers, were made using engraved patterns. So back from Creo back into Rhino, we start developing many different patterns for the covers. Some geometric ones, some more. And we call this one, we call the two. So we have many different patterns that were embossed in the surface of the covers. And so the hand was launched on the market, introducing many innovations compared with the competitors. But still, it was black and white. We used white for the silicon parts, which are the glove and the co-moldings on the fingers, and black for the plastic parts, because those came straight from the 3D printer. But for the project to be really successful, we still needed color. And we were lucky enough to get in touch with HP Labs, and their jet fusion team. At the time, they were in the process of developing the ability to print in color and even in white. And they were looking for companies with such needs and for parts to test their printers. And so we achieved color, and not just color, but pretty much an infinite range of colors, even white. And so today, the hand, today Prensilia has an online configurator where the customers can customize their hands. They can pick the color for all the 3D printed parts, color for the covers. We develop different textures. So the covers can be just smooth with images printed right on top of them. They can be the hand touched, monochrome textures, or even textures with gradients. I mean, any kind of customization is possible, and this is a definite advantage over competitions, because, like we said before, most competitors' prosthetic hands are covered with a black or transparent silicone glove. Next came a new task. On one hand, to introduce always new kind of styles and aesthetics on the covers, and on the other hand, a search for weight reduction, because one of the issues that is present with many of these kind of devices is the weight of the hand, because once you factor in the frame, the covers, the glove, and the mechanics, these hands end up weighing more than a regular human hand. And so that puts a strain on the arm and the shoulder of the amputee. And so we used Grasshopper to research new ways of decreasing the weight of these covers. So we developed two patterns using Grasshopper and their functions. I'm going to walk you through the steps that we took here with Grasshopper. I didn't work directly on this, so bear with me for any imprecision. So for the circles pattern, which is the one we see here on the left, first we created a simplified version of the cover surface of the area where we wanted to apply this texture, and we used the shape map plugin to unwrap the surface and obtain the outline. Then we created a point grid over this outline. We used a bounding box to generate a frame within which to create this point grid, so that the point grid didn't exceed the size of the actual surface. And then we applied circles on this point grid. There is an offset which defines a margin between the points and the shape, so that these circles don't overlap with the shape, exceeding the size that we defined. And here we have a start and end domain which define the size, the minimum and maximum size of these circles. The circles are also defined so that they go from the smaller size closer to the edge to the biggest size further away from the edge. Using shape map again, we applied the unwrap back onto the surface. at this point, we had to start making these holes into the cover. So to do that, we needed some cylinders that we could subtract from the cover surface. But in order to do that, we needed to be able to extrude every circle perpendicular to the surface. And so we used Grasshopper again to extract the center of the cylinder of the circles, and together with their normals, and then project them onto the surface, obtaining this way this series of cylinders, which we then scaled along the z-axis to make sure that they went all the way through the cover, creating what we call the porcupine, which was then brought back into Creo to punch holes into the actual covers. In this case, we had a reduction of 7% of the quantity of plastic, which is not much. But at the same time, the size of the holes is so that it protects the inside of the mechanics inside, and doesn't let like small tips like a ballpoint pen inside too much as to damage the mechanics. So that provides it's a slightly less heavy than before, and it still provides the adequate protection for everyday use by the amputee. One of the uses, though, that the Mia hand is also used for is within industrial production, because where some companies use robotic arms with many different kind of attachment, let's call them hand attachments, to grab and do operations. They've been testing Mia hand as a replacement for 3, 4, even 5 different kind of clamps, because Mia hand can do 5 different kind of grasps with just one single tool. So they've been testing it this way. And so the next cover, for the next cover we used a Voronoi pattern, which doesn't provide enough like protection for everyday use, but is widely used for industrial applications. In this case, we went back to the actual cover surface, to the actual surfaces of the covers that we designed, and we created a surface that sits exactly in between the outer and the inner side of the cover. So while in the previous one we had like a single surface, here this is a poly surface made of like 100 different little surfaces stitched together. So we again used shape map to unwrap the surface and to get its outline. In this case, here you see a solve data node with 2 lines, which we used to define the scale and the position of this unwrap. Then we defined 2 different Voronoi patterns, because like we will see like in the final renders, they had to reduce the size of the holes in the cover but still keep it light. We generate 2 different set of Voronoi patterns. One that we use to make holes towards the outside of the hand, and one towards the inside. We'll see that better later. Here, we created a bounding box, which was populated with random points, which are used to create a Voronoi pattern. The Voronoi pattern it's like balloons starting from each point and inflating until they touch each other, and ends up with a lot of straight lines closing each single cell. So we rounded the corners of these cells and used an offset to create a bridge around each cell of about 2 millimeters. See the offset of -1, which means 1 millimeter on each side, generating this 2 millimeter bridge around each cell. Then we using shape map again, we applied this pattern back onto the surface. Here, for clarity, I'm only showing one of the two Voronoi patterns. So we applied it back onto the surface, and then we had to start cutting, to start generating the solids to use for cutting the surface. In the beginning, we just thought of using these curves to split the surface and then use the solid offset command to do that. But something wasn't working right, and so we had to go through a slightly more complex process to create a normal for each cell. So we took the centers of the cells, created a circle for each point, created a plane going through each circle, and only considered the z-axis of these planes as the normal of each cell. This, in the end, allowed us to generate a whole set of solids, which again we brought into Creo to carve the covers and remove material. So you can see here that there is a set of Voronoi pattern that cuts from the middle of the thickness of the cover towards the outside, and the other one from the middle of the cover towards the inside. This coupled with the ability of printing in color.
I'm sorry, we stopped hearing you. I'm not sure if something happened with your microphone.
Can you hear me?
Yeah, now it works again.
All right.
Perfect, thank you.
All right. So we were able to generate this double Voronoi pattern, and which is highlighted by the possibility of printing in color with jet fusion printers. In this case, we had a 28% less plastic used, which is considerable. It brings a significant weight and plastic volume reduction. So Mia Hand competed in the last two editions of Cybathlon, which is a competition for prosthetics, in which athletes need to perform everyday tasks like opening a door, taking bottles out of a cage, or doing some simple tasks in the least possible time with the least possible errors. And in the last edition, 2024, Mia Hand was ended up in the 4th place. So that was not a bad placement. And so we can see the hand in action. Thank you for your patience.
Looking great, thank you. It's very nice to see how you use so many different tools like SubD for modeling the hand, and then change it to Creo, and then go back to Grasshopper to model the textures. It's
We really
nice.
appreciate this flexibility, and I mean, our design process means that requires that we reach a result. So we use all the tools that we need to get there, and most of the time it's a mix of tools. But the good thing about this, the integration between working with Rhino and Creo, is that we can move geometry back and forth, and that is an added value of both softwares.
Yeah, and using Grasshopper for the textures is really nice, and that you can customize the design is great. Yeah, I suppose that the 3D printing process is also complex, but it's very good to have all these different options and materials and colors. So I think it's a great project.
Yeah, the cool thing about printing in color with Jet Fusion printer is that, I mean, these parts are printed in PA12, which is very durable. And even if you take the color, the covers that are like printed with full pictures matte on them, and you start scratching them, there's still color underneath. So it's like it's quite amazing.
Yeah, I was checking the chat. Many people saying hello from every part of the world, from Europe, from America, from Turkey, I see here. So it's nice, from Thailand. And there are some questions now. Well, many people saying thank you. And Rob Geyer is asking, are you still involved with the hand development, or is that
Yes, I see the questions here. Well, yes, because this is a live project. I mean, the first hand, the one that was just in black and white, was introduced in 2019 with the new, and I mean, and it won the Red Dot Design Award. And then the next generation, the one in full color, was introduced in 2022. Again, like the Golden Compass, the Compassador Award in Italy, which is like it's the oldest design prize still running in the world. So that was very rewarding. So we're still working because the hand being 3D printed allows the Princilia to introduce changes and adjustments on the go. I mean, every single one can be different from the previous one, meaning like containing improvements every time. And one of the areas we've been working on with them are the fingers, which in the picture here we see that they're like the black part is 3D printed, it's plastic, and this white portion is molded in silicon on top of the plastic part. And based on user feedback, they noticed that they need a little more grip on some areas of the fingers, a little less on other areas. And so we've been adjusting or improving the shape of this overmolding over time. So yes, the hand is constantly evolving. This was the very first version of the glove, which had some where the silicon glove had tendency of cracking or breaking up in a few points. So we modified the folds and the shape to improve durability. So it's a constantly evolving project.
Yeah, thank you. Yeah, I was thinking that it's great because one of the first tutorials to learn how to use SAP-D is to modeling a hand. So it's great to see the final result that you obtain starting with SAP-D too. I think it could be great for some of our users that start with this tutorial to see the final product that you can achieve starting with SAP-D. Rob is saying again, from the initial working design launch, what percentage of change to the design have you made to date? You were saying a bit explaining it, but
most of the design is still there. I mean, it's still there. It's still the same. If you look at this, the hand that's on the screen there, or for example, I take or this, which is one of the latest iterations, which is already in full color. If you see my webcam,
yeah.
So we can see. So I can say that 90% of the original design is still there. The changes that we've done are small adjustments to the shape of the glove. For example, you see the way that the glove is cut here for allowing movement of the fingers, and it's different from what you see on the screen, on the white glove on the screen, and the shape and size of the silicone overmold on the fingers is also different, but those are, I would say, little details. The overall look and feel of the hand is still the same. So 95% of the original project is still there.
Yeah. I was looking for the tutorial. I will share it in the chat about how to create a hand with SAP-D because it's really nice to learn how to use it. Yeah, I was taking the other question also from Florin Felix, that he asked, how did you prepare the design for manufacturing if you use Rhino or something or other software?
Well,
Mm,
like I said before, all parts were designed to be injection molded. What we designed in the first phases in Rhino were 3D models that, of course, took into account all the mechanics and the electronics, and that were fitted on top of the frame, and a frame and mechanics that adjusted over time with what we were pushing the engineers to do, and what the engineers said, okay, this has to be like this. So we dressed it on top of all the internals. All the actual parts were developed with Creo. So we took what we can call the glove, the hand itself, over to Creo, and then we started like slicing it up and creating all the parts. So the parts, extraction angles, draft angles, and all that were all done in Creo.
Thank you. Yes, I completely understand. I'm sure if there are any more questions, checking. Okay, thank you so much. Yeah, I think that's all. Rob is asking again if the black part that is 3D printed is also then injection molding or is only 3D printed?
No, well, these pictures
Yeah,
helps
yeah.
understand pretty well, because what you see in black is 3D printed.
Okay.
What you see in white is silicon. So the portion of silicon that is at the bottom of the fingers, the bottom half of the fingers, that is overmolded on top of the 3D printed part. Whereas from this point to the right, everything else is a single part, which is the glove, and which is cast into a 3D printed mold. It's not an easy part to manufacture.
Yeah.
Because I mean, technically, it has more undercuts than moldable parts. But the company that manufactures it they're pretty good.
Yeah.
They've been making these gloves for a few years now, and they're the only company so far that said yes, we can do it, because the Prensilia has different suppliers, and only one of them said yes, we can do it. The other ones saw 3D file and said, you guys are nuts.
Yeah. Okay, so thank you so much. I think that makes it. Yeah, one more questions that Florin asks is about the durability of fingers. How did you address this in the design process?
Well, that's one of the reasons of the changes that we've done. We've done 3 or 4 iterations so far on the fingers. At first, they were overmolded in a softer, in the same kind of like softer, flexible silicone used for the glove. But then over time, the overmolding was not gripping enough on the 3D printed part. So, like if you stick your nail in where the two materials join each other, you could just kind of like peel it off. And so we've experimented with different hardness of silicon. The last iteration, which is the one I'm holding here, doesn't use actual silicon. It's a different kind of soft plastic. To remember exactly the exact specification, but it's not actual silicon anymore. It's like a different kind, to provide a better attachment to the plastic part and a better grip for the user. Because even though this is silicon, being so soft didn't provide enough grip for the user in some usage cases. So they needed a better grip. So that's one of the areas where we've done the most changes, the most adjustments. Because I mean, every patient gives its own feedback, and the project can be adjusted accordingly. One good thing about it is that Prensilia are very interactive with their clients, with the amputees, and so feedback often results in like, okay, send us back the hand. we got new fingers, we replaced them. Okay, try these new fingers, see if they work better. Because not having invested in tooling, but 3D printing parts, they can, okay, look, we just got a new batch of fingers with the adjustments that you suggested. So send us the hand. We replace the fingers. You get the hand with the adjustments that you requested. So that's a very cool thing about this kind of production.
Okay, thank you. There are a few more questions now. Let me check. What was the first one? Let me close this. It's from Mark Briggs. I know that's...
See how many years has the project taken?
Yeah, exactly. Thank you.
And
yeah, if you can read it.
Yeah. I'm very some. I mean, they scroll pretty quickly. Well, we started working on this project in 2018. The design itself took a few months, and the research took a good 2 months. Interviewing with amputees, which at the time, of course, were using competitors' prostheses, and talking to them to understand, like, okay, what they liked about them, what they didn't, and to come up with something that could improve even further their life, because I mean, for an amputee, a device like this is life-changing. And so we want to make sure to get into the project as much of the feedback we got as possible.
Yeah, and there are a few more questions about the size of the hand, if there are different sizes, or if you adapt it, or it's only one size.
Yes, the hand comes in 3 sizes, and the one we worked on is the smallest one. Mm-hmm. Because, of course, I mean, if everything fits in the smallest size, it will fit in the medium and large size too. Yeah. And of course, I mean, this is a right hand. Of course, there's also a left hand version of it, and yes.
Yeah.
And the hand can be scaled to fit different sizes.
Okay, so thank you so much, Guido, again for the presentation. It has been great being able to see the process of the tools that you use. And thanks again for everyone that has attended this webinar. Just remember that it has been recorded. I probably will upload it to our YouTube channel tomorrow, and I will send an email when it's ready if you want to check it again or share it with your colleagues. So thank you one more time.
Thank you all for viewing, listening, and for your questions.
Thank you so much.
Goodbye from Italy.
Bye-bye. Have a nice day. See you.